This video is recorded to present the paper Dynamic Modeling, Controller Design of a Novel Aerial Grasping Robot. In the first section, we will introduce the design concept of our robot. The dynamic modeling and controller design are presented in the second and third sections. The controller is tested in core simulation in section 4. Finally, we will discuss about conclusions and future work. Nowadays, aerial robots are more and more popular in grasping, manipulating, and transporting objects. Those robots are equipped with diverse devices, such as manipulators, cables, and so on. However, most aerial robots cannot perform grasping, manipulating, transporting objects at the same time, especially for large objects. For instance, we need to attach objects to aerial cable-driven robots. Motivated by those limits, the main contributions of this paper are proposing a novel aerial robot for grasping, manipulating, and transporting large objects, and designing a controller which has been validated in core simulation. Flying gripper is composed of 4 quadrotors, 4 self-adaptive fingers, and 1 body structure. We choose self-adaptive fingers to adapt to the size and shape of the object during grasping. Each finger is actuated by gear rotation of 1 quadrotor through a worm gear mechanism. The 4 quadrotors are tilted with respect to horizontal attitude in order to ensure full manipulation capacity in space. The worm gears are chosen to be no backdrivable to produce secured grasps. In fact, when all phalanges are in contact with object, they cannot move backward, whatever external forces are applied to the object. Here is one video to show how 1 quadrotor drives a finger to close. Now, we are going to introduce dynamic modeling of the robot. First of all, the configuration of the robot is represented by a generalized coordinate vector, Q. It describes the position of the body structure, the attitude of the body structure, and the gear rotation angles of the quadrotors. We make 3 main assumptions for simplifying dynamic modeling. First, we assume the fingers are closing, opening in a slow way. Thus, we neglect their dynamics. As the fingers are driven by the quadrotors' gear rotations, in slowly grasping, we can also neglect the dynamics of the gear rotations. Therefore, we consider the whole robot as one single rigid body. In dynamic modeling, we only consider the pose of the body structure as a consequence. We apply Newton-Euler formalism to obtain the dynamic model, which is shown in equation 1. The input of this model is a wrench applied to the body structure by all quadrotors expressed in body frame, which is represented by W. Now, we will talk about controller design. In fact, our robot is over-actuated. Thus, our controller consists in 2 modules. First, a model predictive control is introduced to track reference trajectories. Our allocation algorithm ensures closing, opening fingers during tracking. It is of interest to notice that we cannot measure the object's position and the fingers' configurations, no mention to the object's mass and inertia. Thus, the controller must adapt to those uncertainties and disturbances. For instance, a model predictive control computes the required force of the body range for tracking a reference trajectory. It aims to minimize tracking error during the whole prediction period of time. The allocation algorithm is responsible for computing the control input U, which is a vector of motor speed of all quadrotors. First, it must generate the required body range, which has been computed by model predictive controller. This task is represented in equation 7. Second, it must produce yield torques of the quadrotors in order to close or open the fingers. This is modeled by equation 8. The final allocation problem is formulated in equation 9. We apply the method proposed by Bott in 2009 to compute control inputs. We compute the mean values of maximum and minimum control inputs, UM. Then we use UM to compute the final control input U in equation 10. The controller is tested in MATLAB and Adam's co-simulation. A changing directional disturbance force and sensor noise are introduced in our co-simulation. The masses of the robot and the object are 5 kilograms and 1 kilogram. In co-simulation, we designed a reference trajectory for the robot involving approaching, grasping, transporting, and releasing the object. The robot is assumed to be above the object. As we can see from the video, the controller enables the robot to follow the reference trajectory under disturbance forces and sensor noise. It also deals with the changing dynamic parameters such as mass and inertia. Finally, the object is placed at the desired position. Now, we will talk about conclusion and the future work. The developed model predictive controller based on the dynamic model enables the robot to track a reference trajectory dealing with the very fine dynamic parameters such as unknown mass, inertia, and center of mass. The controller allocation algorithm ensures the closing and opening of the fingers while tracking the trajectory. Simulation results validate the effectiveness of the controller and its robustness against external disturbances and noise. In the future, we will test other robust controllers in high motion control rather than model predictive control. We will study allocation algorithms for energy effectiveness. And also, we will build the prototype and test the controller in real-time experimentations. Thanks for your attention.